Where do we come from? As far as we know, everything began with a singularity, an infinitely small, infinitely dense point in the middle of nothingness that expanded. This event, which we commonly call the Big Bang, marked the beginning of everything we know: space, time, energy, and matter. One of the most popular mental images of this event is an explosion, a sudden boom, but the reality is more complex. Instead of a conventional explosion that sends debris flying into empty space, the Big Bang was an expansion of space itself. Space wasn't expanding into anything. Rather, space itself was stretching, and with it, everything we now see in the universe. In an unimaginably short fraction of a second, the universe went from an infinitely small singularity to something far larger. This period of rapid expansion is called cosmic inflation, and it set the stage for everything that followed. In the first few moments, temperatures were so high that no atoms could exist. Only elementary particles like quarks and gluons, along with the fundamental forces that govern our universe: gravity, electromagnetism, and the strong and weak nuclear forces. The birth of matter: as the universe cooled, quarks combined to form protons and neutrons. A few minutes later, the first atomic nuclei began to form in a process called Big Bang nucleosynthesis. However, the universe was still too hot for complete atoms to form. Electrons were still roaming freely, colliding with photons. This state of hot, opaque plasma persisted for 380,000 years. Then, something remarkable happened. The universe cooled enough for protons and electrons to combine into neutral atoms, mostly hydrogen and helium. This process, called recombination, made the universe transparent for the first time, allowing light to travel freely. The remnants of this first light still exist today as cosmic microwave background radiation, CMBR, a faint glow detected in every direction of the sky. This radiation serves as a snapshot of the early universe, providing crucial evidence for the birth of matter. As the universe cooled, quarks combined to form protons and neutrons. A few minutes later, the first atomic nuclei began to form in a process called Big Bang nucleosynthesis. However, the universe was still too hot for complete atoms to form. Electrons were still roaming freely, colliding with photons. This state of hot, opaque plasma persisted for 380,000 years. Then, something remarkable happened. The universe cooled enough for protons and electrons to combine into neutral atoms, mostly hydrogen and helium. This process, called recombination, made the universe transparent for the first time, allowing light to travel freely. The remnants of this first light still exist today as cosmic microwave background radiation, CMBR, a faint glow detected in every direction of the sky. This radiation serves as a snapshot of the early universe, providing crucial evidence for the Big Bang model. The cosmic dark ages. After recombination, the universe entered a period known as the cosmic dark ages, a time before the first stars had formed. There was no light yet, only a vast, expanding sea of neutral hydrogen and helium. This period lasted for hundreds of millions of years, but gravity was at work. Tiny fluctuations in density, left over from the early universe, caused some regions to attract more matter than others. These regions collapsed under their own gravity, forming the first stars about 100 to 200 million years after the Big Bang. The first stars and galaxies. The first stars, called population 3 stars, were very different from the ones we see today. They were massive, burning through their fuel quickly and exploding as supernovae. These explosions enriched the surrounding gas with heavier elements, which later formed new generations of stars and planets. Over time, stars clustered together under gravity, forming the first galaxies. One of the biggest mysteries in cosmology is exactly how galaxies formed. There are two main theories: the hierarchical model. Small structures merged together over time, forming progressively larger galaxies. The monolithic model. Large galaxies formed all at once from massive clouds of gas. The James Webb Space Telescope, JWST, was launched in part to help answer this question by looking deep into the universe's past. The role of the James Webb Space Telescope. Launched in 2021, JWST is the most powerful space telescope ever built. Unlike the Hubble Space Telescope, which mainly observes invisible and ultraviolet light, JWST specializes in infrared observations. This allows it to see through dust clouds and detect extremely distant galaxies, ones that formed just a few 100 million years after the Big Bang. One of JWST's first major discoveries was that some of these early galaxies were much larger and more developed than expected. This was surprising because, according to our previous models, galaxies shouldn't have had enough time to grow that large. This discovery sparked speculation that the Big Bang model might be wrong. But in reality, what JWST found challenges our understanding of galaxy formation, not the Big Bang itself. Did James Webb disprove the Big Bang? No. The James Webb Space Telescope has not provided any evidence against the Big Bang. Instead, it has revealed unexpectedly large and well-formed galaxies in the early universe. This suggests that galaxies may have evolved faster than we previously thought, or that there are some gaps in our understanding of early cosmic structure formation. Scientific models are not static. They are constantly refined as we gather new evidence. The Big Bang model is not based on a single observation. It is supported by multiple lines of evidence. Cosmic microwave background radiation, CMBR. The oldest light in the universe, precisely predicted by the Big Bang model. Hubble's law, the observed expansion of the universe, discovered in the 1920s. The abundance of light elements. The predicted ratios of hydrogen and helium match what we observe. Even if our understanding of how galaxies form changes, it does not invalidate the evidence for the Big Bang itself. Expanding our understanding, science is a process of continuous learning. The goal is not to confirm what we already believe, but to challenge our understanding with new data. That's exactly what JWST is doing, helping us refine our models of galaxy formation, not rewriting the entire history of the universe. It's important to be skeptical, but skepticism should be based on evidence. Claims that the Big Bang never happened need extraordinary evidence, something JWST has not provided. Instead, it has given us a new puzzle to solve. How did galaxies form so quickly in the early universe? The answer to that question will likely come in the next few years, as astronomers continue analyzing JWST's groundbreaking data. Conclusion: the future of cosmology, the story of the universe is far from over. Every new discovery opens the door to deeper questions. JWST has already transformed our understanding of the cosmos, and its discoveries will shape the future of astronomy for decades. So, where do we come from? We come from a universe that is constantly evolving, full of mysteries waiting to be uncovered. The Big Bang set everything in motion, but the details of how the cosmos took shape are still being revealed. And that is the beauty of science. It never stops questioning, and it never stops searching for answers. Thank you for watching, and until next time.